Hello, everyone. My name is Devendra Kapadia, and I'm the manager of Calculus and Algebra at Wolfram. It's my great pleasure to welcome you to this first Wolfram R&D Twitch talk. It's a series of talks being given by me and other developers from our team, or very large teams. And my goal today would be to talk to you about some recent developments in my own area, Calculus and Algebra, particularly those which relate to version 13.1, which we shipped around a month and a half ago. Now, when we try and ship or plan for a new release of Mathematica, there is a dilemma. Should we really focus on new things, new and fancy things, or try and improve old things? Then our general policy is to have a balance of both in any release. So in 13.1, we have a couple of very new dramatic features and then improvements for old functions which people continue to ask us for. But for sure, I think it's a release which is very much user-driven, based on suggestions from you all over the last 30 years, really. So with that brief introduction, let me now speak about what's new in Calculus and Algebra in version 13.1. So here is my plan for the talk. So in this talk, I would like to discuss the following new features for 13.1. So I guess the main new feature was the brand new features, fractional calculus, which people have requested for the last 15 or 20 years, and we've done it now. But of course, that's a wide area. And what I do is to give you just a very informal introduction, probably for around 10 minutes or so, and then we'll go on to other things. So for example, we have core calculus, the old-fashioned calculus, which has also been improved. And over there, we have the so-called singular solutions for DSolve, which have been requested for the last 30 years, basically. We have new implicit differentiation function capabilities, new things for change of variables in DSolve and integrate, and some pretty advanced mathematics in the form of residue sum from complex analysis. So that's the calculus side of things. And we continue to expand special functions. And here we have some improvements for the so-called centered interval functionality from version 13.2. Now, as a team, we are basically a math team. We are kind of people who love mathematics. So we honestly don't worry too much about how applied we are most of the time. But there's one area we actually do the same kind of stuff that very large software and hardware companies might do, and that is linear algebra. So all the things that my team does, linear algebra is the one case where we intersect with computer science, image processing, artificial intelligence, neural networks, etc. So I'll talk about some recent developments to do with structured matrices in this area. And the other thing that as a goal for our team, we say, okay, we're going to do development, but we also like to do some documentation improvements for every release to make sure that we provide the best possible examples to our users. And in fact, in this release, linear algebra again has taken the pride of place for that. And if that were all we did, then we'd still have some spare time, because really we're an education team. So we need to worry about what do people want to learn from us. We are really the best place to go for learning many things. So over the last few years, we have been developing these online courses for calculus in other areas. I'll talk about recent initiatives. There's been a burst of activity in that area, so I thought I should bring it up because for us, this is part of the regular release cycle. Do some development, do some documentation, do some coursework, and that's the way our release always go. Okay, so I'd like to talk about fractional calculus, but even before doing that, I should do a brief recap of calculus itself, the well-loved calculus from high school and college. So calculus, as you know it today, was developed in the 17th century Europe by Newton and Leibniz. You can see them over there. And they studied the two big operations, derivatives and integrals. So we have a function called d, which does derivatives. The derivative of x squared is 2x. And now if you take that output and give it to integrate and make sure you ask for the arbitrary constant, then you get back almost what you started from. So integration is essentially the inverse operation of differentiation. And this was, of course, the great achievement of Newton and Leibniz, which is why they're called the creators of calculus. And although you might not do it very much at high school or college, you could integrate n times. and then that'd be the same thing basically being a derivative of order minus n. So if you integrate 3 times, that's like a derivative of order -3. So this calculus of derivative integrals has stood by us for a long time, but the point over here that this n over here is just an integer. So question is, what happens if n were not an integer? And that's a question people have asked since Leibniz himself. What is the half derivative of x, for example? And now to really talk about the important question today, which is what is fractional calculus? So fractional calculus generalized derivative integrals to the idea of a fractional derivative, and the word fractional over there simply means that you could have any order. There's a bit of misuse. The fractional way it could be pi or square root of 2, whatever, but you want to talk about derivatives of any order alpha. And this alpha or derivative must have some property. Of course, when you do modern science or mathematics, you want to have kind of backward compatibility. You don't want to have something completely new. So it must be equal to the nth derivative of the function when alpha is a positive integer. So if you do alpha equal to 3, that should be the third derivative. And it must equal to the nth repeated integral when alpha is negative n. So if alpha is negative 3, then you must have the third repeated integral. And for all the orders, it must somehow interpolate between the derivatives of the orders. So you see a kind of figure over here which is worth keeping in mind. So that's the integral, that's a derivative, and all the orders in the middle will somehow interpolate in terms of their graphs. Now, clearly, it's a very loose scheme. So over the last couple of hundred years, lots of people have given their own definitions of fractional derivatives. So there's one due to Riemann-Liouville, which is very important. There's one due to Grunwald-Letnikov, one due to Caputo. And when you study another subject, you realize that the only really difficult part about fractional calculus is remembering all these long names. So the subject is quite simple. So for version 13.1, what we've done is to implement 2 of these, which are kind of most fundamental, and that's the Riemann-Liouville derivative and the Caputo derivative. Okay, so now I can talk about the first one of them, the most important one from a foundation point of view, that is the Riemann-Liouville derivative. Okay, so we have a new function called fractionality. And what fractionality does is it computes a Riemann-Liouville derivative of function 13.1. So this derivative is kind of a mix of d and integrate. So you do some integration over here, you do some differentiation over there, but how much you do depends upon the value of alpha. So you see over here, you've got a series of alpha. Alpha could be any number, and n is an integer. So this over here is the formula for Riemann-Liouville differentiation. So you might ask, okay, what's the half derivative of x squared? So you say fractionality x squared and the half derivative. And this is a really strange looking answer. Why would that ever happen? Well, you go back over there, the definition say, okay, alpha is 1/2, so n is 1, so you must do one derivative and some integration. So apply definition, and the gamma half is what we're going to give you the square root of pi. So that's the same answer. Now, if you show it to an engineer, he's not going to believe you. He's going to say, I don't believe you. So what we do now is we're going to look at the next thing over here, which is, can we do 2 differentiations and get back to the well-known answer, which is 2x? So if I do a first half derivative and second one, 1/2 plus 1/2 is 1, so you get back 2x, which is quite remarkable. So it looks like this is a nice, consistent calculus. But you might say, okay, can you compute the derivative of an arbitrary order alpha? Sure, we can. Can you make a table of values? Sure, we can. So let's make a table of values of the -1 derivative, the integral, the first derivative, etc. Okay, and you go in steps of 1/2. Okay, and now if you see, you can actually plot, and when you do that, you get back exactly the picture which I showed you in the earlier slide, that interpolation picture of going from the derivative to the integral. So that's the Riemann-Liouville derivative. So before going on to anything else, just a few more examples just to dazzle you with the power of fractional d. So what's the derivative of sine x? Now, if you know calculus, it should sound like cosine x. Not really. The answer is a hypergeometric regularized function. Ooh, that looks pretty bad. So you make a table of values from -1 to 4, and now things look much more understandable. And you might ask, what about this one over here? Well, the one over there is just the integration constant. Okay, so then you can say, that's all great, but what about the derivative of a constant? And that's where trouble begins. So if I do the derivative of constant c, I don't get back 0. If you make a table, you'll see over here that you might have some zeros at integers, but not general. And therefore, you need a more flexible definition for the fractional derivative. And this is provided by the Caputo derivative. So the Caputo derivative overcomes this limitation of the Riemann-Liouville derivative. The derivative constant must be 0 at least for positive orders alpha. Okay, so now on to the most useful fractional derivative for us, which is the Caputo fractional derivative. So the Caputo derivative is computed by Caputo D in 13.1 as defined by this formula over here. So C stands for Caputo, R for Riemann-Liouville. That's the Caputo definition, Riemann-Liouville definition. And what you see over here, you're taking the Riemann derivation and then subtracting off some terms which involve the derivatives at 0. And that's what is required for things to work really well. So this Caputo D is very close to fractional D, but it's much more useful for solving practical problems. So first question, what is Caputo D of a constant? And you get this comforting 0 over here for positive values of alpha. And compare it with fractional D of the constant, and you don't always get that. So the good thing about Caputo D is it recovers for you this feature that the derivative of constant is 0 for positive alpha. But a much deeper reason for using Caputo D is that, in fact, it interacts with the Laplace transform. So let's just clear it in case I've done something with it early on. And let's say you're doing college differential equations, and someone asks you, what is the Laplace transform of the third derivative of x? Then that answer over here is what you'd see. It's got the S domain, the frequency domain over here, and you got the derivatives at 0, the initial values. And what you get back basically is something like a polynomial in S square, S cube, etc. And if you do the Laplace transform of Caputo D of order 5 over 2, very close to 3, then you get back something very similar, but now you get back fractional orders of S. So Caputo D is very similar in its behavior to the Laplace transform, but not quite, because you have these fractional powers of S coming up. So the question is, how do we tackle those fractional powers? So you need a function whose Laplace transform is something like a fractional function. And that function is the hero of fractional calculus. It's called the Mittag-Leffler function. You know, we've had Mittag-Leffler since version 9, but never quite knew what to do with it. And now we do. So Mittag-Leffler is defined by an infinite series, like over here. And if you look carefully, it looks like something like the exponential series, but a bit more general than alpha over here. Okay, so special cases. So if I do Mittag-Leffler of 0, so the alpha is 0 over here, gamma of 1 is 0, gamma of k is 0, so here, so you get just the geometric series. And if you put alpha equal to 1, then you get back the exponential function. And if you do alpha equal to 5 over 2, then you get back a huge expression in terms of PFQ. So Mittag-Leffler is certainly a kind of special function, but on its own, it's not general enough. In fact, it's a special case of the mighty Fox H function. So that's Mittag-Leffler of square root of 5. Does nothing to do function expand, but if you go to Fox H reduce, then it gives back the expression for Fox H. So Mittag-Leffler is the central function of fractional calculus because it includes the exponential function, and it goes far out enough that you can do fractional calculus with it. But the important point over here is, what is the Laplace transform of Mittag-Leffler? Keep in mind that we are hunting for a function whose Laplace transform is a fractional function. So if I do the Laplace transform of Meta Leffler over here, this mess over here, and you see why in a few minutes, then I get back a fractional function. So here you are. That's the key to doing fractional calculus. Use Meta Leffler E for all your work. Now, the denominator over here is a fraction of an algebraic function. So I ask, what are the zeros? There are two of them. I do a complex plot. You see there are two poles over here. And then if I do an inverse Laplace transform over here, then I get back the same Meta Leffler. So Meta Leffler is what lets us bridge the gap between classical calculus and fractional calculus. And now I'm ready to talk about the most important applications of fractional calculus, namely fractional differential equation. So DSolve has forever solved ordinary differential equations, partial differential equations, but in version 13.1, we can also solve linear fractional differential equations with constant coefficients. And almost any of them, not all, maybe. You may have missed something over here. So here is a typical example, but instead of D, you have a capital D, and you could have any order over here, like 2.1 in this case. That's a constant over here. That's a linear ODE constant, well, it's a linear fractional differential with constant coefficients. I give some initial values. I take a Laplace transform, plug in the initial values, solve the Laplace transform, do an inverse Laplace transform, plot the solution, takes a bit of time. And that's the Meta Leffler which you saw on the previous slide. It looks almost like an oscillating trig function. And then what you can do is, just to satisfy yourself, you can do the same thing with DSolve, and you see over here that you just get back exactly the same answer. So what lets us do these fractional differential equations is Meta Leffler with any fractional powers in its second term. Okay, we can go a step further and talk about fractional systems. So you can DSolve can now solve any system of linear fractional differential equations with constant coefficient 13.1. And here there are two methods. There is a classical eigenvalue method and also the Laplace transform method. Okay, so here's a system of equations. That's a matrix over here. So you say vectors, and now DSolve knows, okay, I have a matrix system of fractional differential equations. Now, if you're doing ordinary calculus, then the derivative of sine is cosine, the derivative of cosine minus sine. So the answer would be like sine and cosine, something of that sort. In this case, oh no, we got this big mess. You plot it, and now it looks hopefully a little more understandable. There you are. It's almost oscillatory with a bit of damping. You plot it. I didn't know what the answer would be when I did it the first time, but I was surprised to see that in fact the answer in this case is, well, you'll see in just a minute what it is. It's a spiral. So this beautiful spiral is a solution for the most basic system of equations in fractional calculus. And I was rather amused to see that people have actually made the new fractional calculus work also for PDs, although we never intended that to happen. Okay, so sometimes you do things and you don't expect some development, but they do happen. Okay, so with that, I can now go on to classical calculus, and the first theme over there is singular solutions from DSolve. Now, so Mathematica 1 shipped in 1988, and around 1990, the first request for these singular solutions started to come in. There was Jerry Kuiper, who in fact was kind of the father of numerical computation in Mathematica. He said, you're missing this singular solution from DSolve. We didn't pay much attention, I wasn't there, but okay, as time went by, people asked more and more, and in fact, they've asked for two kinds of solutions, the so-called envelope solutions and the so-called equilibrium solutions. So what's the difference over here? See, over here you have a family of straight lines crisscrossing, and the parabola over here, that parabola is not really a straight line, of course, but it's a kind of limiting case of that family of straight lines. So it's a singular member of that family. It's a limiting case of that family. And here it's the kind of plot you might have seen, your governor of your state during the COVID pandemic, where you have these curves showing you the vaccination effects on the population, and things start out zero, they quickly increase, and then stabilize once people start getting vaccinated. So that's what we call an equilibrium solution, the equilibrium state for any population. So if we just do a D-solve for a nonlinear first order ODE like this one over here, it's nonlinear, then what you get back is just the general solution. In fact, this is exactly the solution over there. It's a family of straight lines depending upon C1. As you vary C1, you get the different solutions over here. Okay, then you could say include singular solutions goes to true. And now we get back that additional parabolic solution. So singular solutions are a long-time request, and what you've done is to introduce them in version 13.1, but a little carefully, it's an option because we realize that this is a very expensive computation. It's like searching for a needle in a haystack. It's taken us 30 years. I think that anything we do with it is, I would honestly say, very, very risky beyond what we've done right now, but we continue to develop this. But it's nice to see a 30-year-old suggestion falling in this new release. Okay, so now I go on to something much more familiar from college calculus, and that is implicit differentiation. So implicit D in the new release can be used to compute the integral implicit functions. So here is a curve, and you want to work out the slope of tangent line. And of course, you could do it by hand. You could ask Wolfram alpha, but implicit D is much more powerful. It gives the answer for this and a wide variety of inputs. So this answer here is the slope of the tangent line at a point xy. Then you can pick a few points over here with fine instance, like I've done over here, plot them at the slope, and what you see over there is this beautiful picture of a curve with 6 of its tangent lines. And I should mention that this will also be useful for checking solutions from D-solve, which is always a problem for us when they are implicit solutions. So implicit D is a new function in 13.1, very useful for, I would say, what we'd call in this country, calculus 1. But then if you do calculus 1, you might want to go on to more calculus. And so when you go to calculus 2 or 3, one topic is the method of substitution or the change of variables and integrals. And we have a nice new function, integrate change variables, which can do that for you in the new release. So this new function works on a large number of inputs, indefinite integrals, definite integrals, and also multiple integrals. Okay, so a simple example, I give it an inactive integral. You see it's inactive over here. If we didn't do that, nothing would happen. So I say, here's the trig integral. What do? You put t equal to sine x, and things cancel out, basically. So if you apply integrate change variables to it, then what you get back is what you get in calculus 2 after substitution. And you might want to check what the answer is. So you can do an activate, which is the inverse of inactive. You get back 1/2, which is correct in this case. Or you could simply compute your integral and you get back the same 1/2. But then you could get a bit more ambitious and talk about calculus 3 and talk about the change of variables for multiple integrals. So here is an inactive integral, which is in 2 dimensions. Okay, so I create it. That's a familiar example from from the calculus 3, I would say multivariate calculus. And the question is, how do you solve it? Well, obviously, what you do is to switch to polar coordinates. So you tell this change of variables function, Cartesian to polar, and I get back this beautiful simplified integral. So this might take you a couple of minutes to do it by hand, activate it, and you can check the answer again using the old-fashioned method, which is just integrate. Okay, so let me do that over here, and I will get back the same answer. So this over here shows us that we actually have a nice new way of doing change of variables. But people don't want to just integrals; they also want to do differential equations. So over a number of years, people have written their own little change of variables in differential equations. So we said, let's try it ourselves. So this new function of D-solve change variables can be used to apply change of variables in differential equations. And this is quite a powerful function, works for both ODs and PDs. Yeah, I do see some questions coming in. I'll try and find time for them at the end of the talk. I promise we'll try and get to them. But for now, let me just pursue a little bit more and talk about this wonderful thing called D-sort chain variables. It's pretty non-trivial. So if you do a first order differential equation, when you've got past constant coefficients, then they'll talk about the so-called Cauchy-Euler equation, which is one standard example of a differential equation which is not constant coefficient, but can be reduced to one with constant coefficient. So I say D-sort chain variables, that magical function, that's the input, inactive input. I say set x equal e raised to t, or maybe in college you might say t equal log x, doesn't matter, and you get back this beautifully simple answer. So I think it's very elegant that something as complicated as this gets done automatically by the new function. And I recall when I was a student probably in my master's, the professor loved, I would say, like troubling us maybe with hard chain of variables. They does take the Laplace equation in so and so quantum system and transform it. Well, of course, to do that was hard enough, and those days even hard to get a place to check them. But now with these sort of chain variables, you can at least check your answer for this Laplace equation in polar coordinates, going Cartesian to polar, and you get back. When you do this, you get back this wonderfully simple expression. Okay, so my point over here is just this, that we have these new functions which should be quite useful for not just calculus, but beyond that for differential equations. And now I'm going to go a step further and put my feet into something that's really, really difficult, which is complex analysis. So here's my 2-minute introduction to complex analysis. So complex analysis is, for the major part, concerned with the study of what are called holomorphic and meromorphic functions in the complex plane. Those are big words, but that just says that either you might have a function which has got no issues, holomorphic, or meromorphic would mean that there are a few singularities. And there's a famous theorem in complex analysis called the Cauchy residue theorem, which will let you compute integrals of complex functions along curves in the complex plane. And the key to that is to compute the sum of what are called residues. So residue sum in the new release will compute the sum of the residues. What's a residue? Well, it's the first term, the first bad term in the series expansion of a meromorphic function. Okay, so here's an example. That's a function, a complex function. And you want to compute the integral of this function along the circle with center at the origin and radius 2 in the complex plane. So this example is from a book by Churchill and Brown, a very popular book. So what does the function look like in this area? Let's see. Let's plot over here. And that, in just half a minute, is the plot on the title slide for today. So you see there are 5 singularities over here, 1 from here and 4 from there. So what residual sum does, it will just compute all of them for you and add them up in a flash. And what the theorem says, this famous theorem, is that if you do 2 pi I times that, then you should get back the integral along that contour. And you can check the answer with symbolic integration. This is exactly what we've been doing since 1990 internally. So that's the conversion to exponentials, integrate, and you get back just the same result. So the residue sum essentially reduces about 3 chapters of complex analysis to 1 single function. So I think it's a very nice achievement. It's not something that came out in a day. It's taken 3 or 4 releases to come to this point. And we, of course, want to go further and do some more complex analysis in the near future. Okay, so now I've finished the calculus portion, and I now go on to what I talked about early on, which is improvements for linear algebra. So, when you work with linear algebra, it's often very easy to specify a matrix and very hard to actually work with the output. So these matrices are called structured matrices, like the identity matrix can be specified by just the order. And what we've done in version 13.1 is to introduce these 6 new special structured matrices. So these matrices will not give you the answer straight away. They'll return something called a structured array, which kind of encodes the answer, but doesn't give it to you unless you are eager for it. So the point is that these have been optimized for all kinds of operations. So here's a popular request from users: give me a block diagonal matrix with that block and that block. And you see, get back over here, this blob over here doesn't look very nice. But if you do a display in matrix form, it looks just like it would if you would actually write it out. Or you could even do an array plot. You could compute its determinant, or its trace, or its inverse. And what you see over here is that when you do the inverse, we actually get back another block diagonal matrix. Now, the nice thing about these matrices is that they know a lot about them. They are self-aware. They're like intelligent matrices. So you can ask this matrix, okay, what are your properties? It'll tell you, I know about my blocks. I know my permutations, what have been done to make me nice and structured, etc. So then you can ask it, okay, go ahead, tell me what your blocks are. And sure enough, it'll tell you what the blocks are from the definition. Then you can ask it, okay, what are you good for? And it'll tell you, I'm good for so many functions. So each of these matrices have been optimized for a very large number of linear algebra functions. And the point is, now you have a kind of structure which is recognized as the whole system and makes things really easy. So you might get like 100-fold speed up for anything over here. Okay, so our plans to add more structured matrices in the near future. Okay, so I still see questions coming in. I promise I'll take them later on. I saw one from Ali Hashmi. I thank you very much, but just give me a few minutes, I'll wrap up, okay? So that's the structured matrix program, to try and build back these efficient structures, which can then be used by ourselves and by people outside, and eventually to let you build your own structured matrices. Okay, so now on to special functions. So we had this thing called centered interval in version 13.0, which we applied to 100 special functions, and that basically lets you work with not just a single number, but a small interval around a number, like in this case, a center 2 and a radius of that. And we have a design review for each of these every release. And Stephen Wolfram said, why do you also do this for interval itself? So interval is an old function of version 13.3.0. And so in version 13.1, thanks to him, we have this support for the same special functions, but with interval, the old-fashioned interval rather than centered interval. And then we put this for testing, and one of our internal testers said, why don't you use function expand to try and expand the scope? Like over here, you see Haber sign is basically a cosine, so now we can do the interval arithmetic on Haber sign as well. So basically, thanks to our internal testing, curiosity, what do we call it, we actually have support for 136 functions using interval in just the space of a few months. So my point is that we do listen to people, both internally and externally. We can't always listen to everyone and implement what they say. Sometimes it takes 6 months, sometimes 30 years, but I promise you, we do listen to you. Okay, so I've mostly finished with the algorithms, and I now go on to an important theme for us, which is documentation. So we've been working on these linear algebra functions for the last 2-3 years, and now we finally finished an update for around 50 linear algebra functions for 13.1. I did this online course, which is quite popular, and I found our documentation really was, I would say, almost out of date, sorry. But now we've got beautiful examples for things like eigenvalues, eigenvectors, for people to learn about them and use them effectively. So that project is now done, and now we are doing the next major project, which is to add application examples to around 250 special functions in the system. Okay, so documentation continues to be an important thing for us, but for me personally, I've at an early stage of my career actually have taught. I was a classroom teacher, so I love teaching. So we are always thinking about the next online course. So in January 2022, we released this course on differential equations, which has been quite popular. In fact, it's doing really well. And now to go further, we're going to be a little more ambitious, or what we like to call it. We're trying to release a course on elementary algebra for middle school in September, October. There'll be a study group in September to which we hope to invite the local and other middle school, high school students. and we will teach them algebra using the Wolfram language. As a math teacher, I can tell you that if you could conquer the teaching of algebra, we'd be good for the next 50 years. The fact is, in this country and maybe elsewhere, people struggle with algebra and then they struggle with calculus, and then we struggle with computer science. If you could do algebra correctly, we are done. That's my view. Okay, we also have an excellent course on multivariate calculus coming up. Tim McDevitt, who's very brilliant, is working on this. So that course should be coming up in the next 6-8 months. It's a difficult course. He's working on it very hard. But to me, and to Roger Gurmanson, the director of R&D at Wolfram, we both really want to push ourselves beyond calculus algebra itself. So we plan courses on probability and little circuits. So right now, we are about to finish the first bit of probability course on central limit, all that. So this should be an excellent course using our own probability and statistics functionality. And I'm not an engineer by any chance, but I certainly know some of the circuits. So we are trying to combine system model and Mathematica, calculus and algebra to produce an excellent course for everyone to learn about circuits. So that's a very big plan we have for the next year. It's a very busy time now. There are about 5 people working on different courses, but it's also very exciting to see that this initiative began about 5 years ago is now really taking fruit, and we are really seeing good results from it. Okay, so I really am done, and it's time for me to thank you all. We did have a post on community. We tried to tell people about it. It's great to see people interested in what we do. I'd like to thank Charles, Lou, and Karen Gasha, who've been working hard for this series of talks. The team that I work with is wonderful. We've had COVID. It didn't affect us. They are the most spirited lot I have worked with ever. And much of what you saw today, in fact, almost everything is their work. I'm just presenting it on their behalf. So it's been great presenting to you. We are not thinking of 13.1, we're thinking of 13.2, but that's for a later kind of time. So for now, I'll just close over here and say thank you very much to you. And if there are questions, I'm going to look at them and try and respond to them in just a minute.